Hello. So today we are going to discuss about light in cavities. So we are going to build up laser step by step. So we first look at radiation inside cavities where we impose some boundary conditions. Then we will look at atoms separately and look at how light interacts with atoms. And then we'll combine the two and put atoms inside a cavity and thus go on to construct the laser. So the first part of our mission is to understand light inside cavities. Now cavities uh, are typically, the common characteristics of cavities is that usually it's a linear device. There is a tremendous amount of advantage for actually coming up with a linear geometry for the cavity. And by linear I mean that there is always a long axis along which radiation propagates, right? So this is the longish axis about which light is propagating. And in the other perpendicular directions, there is no confinement of any kind. There is no single best design for the cavity. For example, a cavity like this, which I have drawn, this particular cavity would have a solution of the electromagnetic wave which basically supports a standing wave pattern. You can have cavities which are of this kind, right, which are called ring cavities, where I have arranged, let's say, 3 mirrors wherein light can propagate clockwise or counterclockwise within this cavity. And here the spatial distribution of the fields going around are basically akin to traveling waves in comparison to here, where the solutions are standing waves. The boundary conditions imposed are such that they turn the solutions into standing waves, and whereas here it will be traveling wave. Now there are all kinds of cavities. So there are stable cavities. That is, if you put in light, the only way the light would escape is because of the finite reflectivity of one of the mirrors, uh, and there is simply no other way for the light to walk away when the light is in the mode of the cavity. On the other hand, one could also have unstable cavities, which in themselves are quite useful. These are utilized uh, when you have high power lasers, where you want the light to experience a large gain uh, only for few passes through the uh, active medium or the gain medium, and after a few passes the light is the cavity is designed that the beam simply walks off from the cavity. So there are this variety of possibilities for cavities. We will look at notions of stability but slightly later. uh, but first let me just come to this very fundamental aspect, fundamental ideas of electromagnetics, which is imposing the boundary conditions, the number of modes supported by the cavity, and so on. So what I'm going to look at now is basically the advantage of such open cavities. All right. So to consider this problem, what we first assume is that I have an empty cavity. The empty cavity is an approximation that one would make. For example, this would be a very valid approximation if you are looking at a gain medium which is very sparsely distributed within the cavity. But at the moment, for simple considerations, let us look at a cavity which is empty. So there is only radiation contained in the cavity and there is no matter. Right. So I will not worry too much about the shape, and we will find that it really doesn't matter what the shape of the cavity is. So for simplicity, I will use the Cartesian coordinates, right, which is x, y, and z, and I am looking at a cavity which is rectangular in shape, right. I've got such a cavity. That is, the light is confined in all 3 dimensions inside such a cavity. Now you see, when I say something is a cavity, what I want is that the mirrors of this, or rather the surfaces that enclose the cavity, are such that they are perfectly reflecting. That would mean that uh, perfectly reflecting cavities are those which are made of, for example, in the idealized situation, a perfect metal. That would imply that this metallic walls of this cavity have got conductivity, right, which is tending to infinity. Now you see, uh, clearly, if I have such a cavity, this imposes a certain boundary conditions which are governed simply by Maxwell's equations. I would urge you to look at, to basically revise your knowledge of Maxwell's equations and actually derive for yourself the 4 different boundary conditions which basically govern the electric and magnetic field components of fields across 2 media. So in this case, what we have is the inside of the cavity, which is empty, vacuum, and the outside of the cavity, which is this metallic surface, which has got perfect conductivity. So there are 2 boundary conditions for the electric field that we need to impose. One is that the components uh, parallel to the interface, parallel to the surface, are actually continuous, right? And the second boundary condition, let me write it down, E1 parallel is equal to E2 parallel. These are the electric fields in medium 1 and 2. And the second boundary condition is that epsilon 1 E1 in which we are talking the perpendicular components now, and epsilon 2 E2, if any, this is dependent on the surface currents, or the jump is dependent on the surface currents that might be there on the surface separating these 2 media, right? So these are the 2 boundary conditions. So in case of perfect metals, you would recall that the current density is related to sigma times E. And I just mentioned for a perfect metal, my sigma is going to be infinity. That would mean even for extremely small numbers of uh, extremely small values of the electric field, you will have infinite amount of current, right? And this is certainly completely unphysical. What it imposes is that the electric field inside of the conductor becomes 0. That is the only way to satisfy this relationship. And because of that, given the first boundary condition, it also implies that the electric field basically goes to 0 at the surface, because in the 2 media the parallel components uh, have to be equal, right? So what happens is that the electric field actually gets pinched to a value 0 at the surface, and the electric field component which I am talking about is the component which is perpendicular to the uh, direction of propagation, or rather parallel to the interface which is separating the two media. So if I think about it in 1D, what I would get is, you can think of, let's say, the electric field which is varying. So you see, at precisely the interface, the electric field would vanish, which satisfies the boundary conditions on either side of this. So this is my vacuum, and this is my perfect metal. So what you have is that the electric field actually going to 0, and hence the kind of solutions that this would support would be of such a nature. So let us just, for simplicity, think of it in think of a wave which is, let us say, polarized along the x direction but is traveling along the z direction. That would mean that such a wave, so in my picture here, uh, this propagation direction would be z, and this direction, for example, the wave is, let's say, within the plane, and this direction is x, right? So imagine such a wave. in that case, a simple solution, the z dependence of this can be written down as a times sine kz, kz being the z component of the uh, propagation vector, times z would be the spatial dependence of the field that will satisfy the boundary condition if we choose our kz properly. So imagine, so in our situation, what I'm looking at, that I have a mirror, let us say at z equal to 0, as well as a mirror. There's, I'm drawing part of the cavity which I've drawn earlier, and this now supports an electromagnetic wave which is so. So let me look at a one-dimensional perspective of this three-dimensional cavity. This cavity, this part of the cavity is of length, let's call it L, right? So you can see that if I write down a solution of this kind for an electric field that is polarized along the x direction, in such a scenario, if I choose my length of the cavity to be such that it is an integer multiple of half wavelengths which can fit into this, in the schematic that I have drawn here, what you have is precisely two wavelengths are fit in. So uh, this number would be 4, n would be 4, which precisely fits in 4 half wavelengths within a length L, right? So this, let us just rearrange. Remember that my k, and in this our case the z component, because we are looking at a z propagating wave, the kz is basically, by definition, it is going to be 2 pi by lambda. And you can clearly see that in our situation, my L happens to be, it's related to lambda. So I can as well write this as 2 pi divided by 2 times L multiplied by n here, and that gives me kz of the kind which is n pi by n, right? So this is the kind of, if I choose such a propagation vector, then you see that such an electric field is going to satisfy the boundary condition and hence feel sustained within such a cavity, and such a field would bounce back and forth within this closed enclosure as it is a supported mode of such a cavity. Now let me be careful. So let me call this L as Lz, right? So that will make everything more precise, right? And this is my xyz direction. So the length along x is Lx, the length along y is Ly, and the length along z is Lz. And this is what I had in mind. All right. So if you look at such a cavity, now let us do a simple counting problem. You know that it's an electromagnetic wave. So when I'm traveling along z, I can either be polarized along x or polarized along y. And the same kz would support essentially two modes, two different modes, which are, because they have two different polarizations, which support the same spatial dependence, right? So similarly one can come up with constraints, just like we have constrained the z component of the propagation vector. One can come up with constraints that can be imposed on the kx and ky component, which uh, based on symmetry would be similar. We can have L pi by Lx as a constraint on x, M pi by Ly, and the N pi by Lz. Remember that L, M, and N take only integer values. This would ensure that the electric fields that have, similar spatial dependence involving kx, ky, and kz would actually satisfy the boundary conditions at all the 6 surfaces. There are 2 surfaces in every dimension, so there are 6 surfaces, and at all the 6 surfaces this boundary condition would be satisfied. Right. So now let us see what are the supported possible frequencies that such an electromagnetic wave can have. Now let us be clear that my vector k, which is my propagation direction in an arbitrary direction, it has got a magnitude, right? For this, it has got a magnitude which is 2 pi by lambda, right? Which is the wavelength of the light. And this we have written down as components along the x direction, along the y direction, and along the z direction. So this is precisely what we mean by the fact that I am resolving this propagation vector in 3 different directions. So what I'm writing down is the frequencies which are supported by such a wave. So this frequency is nu can be written as c over lambda, right? Which in other words is simply k times c by 2 pi. Remember that 2 pi by lambda was k. So here what I mean is that this overall value is k. That would mean that I can write down my nu as c by 2 pi times square root of kx square plus ky square plus kz square. I can do a little bit of algebra. You can clearly see that pi by L or pi by Lx, pi by Ly, these are common. And let me look at a simple scenario. You need not, but let me look at a simple scenario where I'm assuming that Lx equal to Ly equal to Lz equal to L. So this would give me that my nu is c by 2 pi times pi by L, which comes out to be a constant, and now there is L square plus m square plus n square. These are all integers. In other words, I have my frequencies. Not all frequencies are allowed, and these frequencies have a label. I will call them as L, M, N, right? And these are simply c by 2L square root of L square plus m square plus n square. Okay, so now that we have such a cavity, let us first get some numbers in. Imagine we are looking at a microwave radiation. You know that for microwaves, the typical wavelength lambda is of the order of 1 centimeter, right? Now let us see what are the kinds of modes that such a cavity would allow. So I can write down just like this. I can write down lambda LMN. What are these? They are simply C by nu LMN, which by the way is simply C by 2L by square root of L square plus M square plus N square. Let me now pick up a microwave cavity whose length is also of the order of a centimeter, right? This is a reasonable small cavity for microwaves. So when L is of the order of 1 centimeter, you will see that the lowest possible mode is when I will write down the complete solution slightly later. You can take it from me. The lowest possible mode supported by the cavity is when at most one of these indices is 0, whereas other ones are finite. So I'm looking at lambda 110, which is a mode with L equal to 1, M equal to 1. That is, you have the kx and ky component, whereas the kz component is not there. Similarly, you have the 101 and you also have the 011 mode. All of these 3 modes are degenerate in the sense that they have the same frequency, and you can clearly see if I put in these values, I would get basically 2 by square root 2 in centimeters, so basically 1.414, centimeter is going to be the lowest possible wavelength. The lowest possible wavelength is the one in which you are essentially fitting in, if you like, only half a wavelength within the cavity in a one-dimensional case. In the two-dimensional case, it involves that you are fitting in the lowest possible mode is the one in which you have the wave confined, for example, in the xy direction. The lowest possible configuration you would have is having both kx and ky to be finite uh, for such a wave, right? And so the next higher mode will be when I choose 1 1 1, that is another possibility, and which is going to be 2 by square root 3, and this roughly is 1.15, right, centimeter. And similarly, we can look at, you understand that one can have the next order mode, which would be, right, lambda 210, which will be degenerate to 012, 102, right, 201, and so on and so forth, right? So one can basically come up with a series of numbers. So let me plot this, my lambda scale. I'm trying to get to a particular point, and my lowest possible wavelength is 1.41 centimeters, allowed wavelength. My next possible wavelength is 1.15. After that, you can keep calculating this. You will see that you will start getting 0.89. Then you will start getting 0.82. And these modes will become closer and closer to each other as we calculate the next higher modes, right? So you can see that the modes are reasonably well separated. If you think about it, there is roughly about 18% or roughly 20% of spacing, right? 20% spacing between these two modes. So if I create such a microwave cavity, I have the possibility of selecting one of these modes as my lasing mode. If I choose such a microwave cavity of 1 centimeter, I have a possibility of choosing one of these modes to actually be sustained within the cavity and not allowing the other modes to be selected. But as we go to smaller and smaller wavelengths, right, a higher and higher frequency, the modes get more and more crowded, and you will see that by the time we reach optical frequencies, so if this is 10 to the power minus 2, these numbers have to contribute at least 10 to the power of 5, right, for us to get to optical wavelengths. This is very important. If these numbers have to contribute 10 to the power of 5, you will see that the L square, M square, N square have to be of the order of 10 to the power of 10, right? So LMN themselves are of the orders of few lakhs. There you see, if you move in integers a little bit, you see that the modes get extremely crowded. Okay, so as a parameter, a good parameter to think about is this delta lambda over lambda, right? So this number, for example, between the first two modes will come out to be 0.26 divided by 1.41, as mentioned to you, is about 18%. So let us take this exercise and try to count the number of possible modes which are there in such a three-dimensional cavity. Remember that one could be in this space wherein you have kx, ky, and kz, which are possible modes, and then these take essentially integer values, as we know, correct? So you see, in such a space, so-called physicists love to call this as the momentum space, you see that every point in this space is would have three indices, which are basically the indices. So the spacing between these is pi by Lx, pi by Ly, and so on, right? Pi by Lz. In this direction, here the spacing is pi by Lx, and similarly here the spacing is uniform, which is pi by Ly. And you see that these various values is basically as you change the integer L, the integer M, if you like, and integer N, if you like, in this scenario. So every point is labeled by this NL, N, L, and M, and you are asking that if I give you a frequency nu, then what are, that is the maximum frequency nu, then what are the number of modes that are possible? So we will do the counting in this space, because even though there are infinite points, mathematicians would call this as countable infinity. So one can actually count the number of modes within a frequency nu, right? So let us look at this. So we are in the K space. Remember that. So the way to implement the counting would be that I look at a surface, right? Let me be more clear. I will look at a surface this surface encloses all the possible modes. This surface denotes essentially, uh, the fields with frequency nu are on this surface, and the all the other lower frequencies are contained within it, right? So what I'm going to do is basically calculate now the volume, right, and divide by the spacing between the points, because I know the volume, and I know the volume within which one point lives, right, because there is an integer spacing between the next point. So I know the volume of individual point, I know the volume of the total sphere, and with that I will be able to get to my the number of modes which are there. So we know that K in terms of nu can be written down as 2 pi by lambda, right, which is 2 pi C by nu. So you see, if I'm looking at a frequency nu, then my number of modes which are possible is basically the volume of a sphere which is enclosing of a frequency nu. So the volume of the sphere will be given as 4 by 3 pi times the radius of the sphere being k, the maximum value of k, which is 2 pi nu by c whole cube, right? Now remember that we are looking at values of n, l, and m, which are integers, but they are positive integers, right? Because if you recall, we had only standing waves which are possible in such a medium. So there is no notion of a negative integer sitting there. So we are looking at, if I'm looking at a sphere in 3D, but I'm looking at only the positive quadrant of such a sphere, then I have to multiply this volume by 1 over 8, right? And similarly, you will see that I have to, for every wave, remember I told you clearly, we wrote down, for example, the x polarized wave. There is an equivalent y polarized wave which is possible, right? So you see that for every k vector, there are two possible polarization directions, right? So I multiply the number of modes as multiplied by 2. So this is the volume and the number of modes allowed there, and then I divide by the volume of individual of the individual point, which, as you know, is simply pi by L whole cube, right? Because pi by L is the separation between individual points. So in a volume pi by L whole cube, we'll have basically 1 point. So you see, this gives us a very nice way to estimate, for example, what is the number of modes. And if you do this calculation, just you do this algebra just a little bit, what you would get is basically 8 pi by 3, and you will see that these pi cubes get cancelled. There is a c cube hanging at the bottom, and this L cube, I am writing down L cube as the volume of the cavity. So this becomes mu cube times the volume of the cavity. So this is the number of possible modes within such a cavity of volume V, and you can clearly see that for a large cavity, the shape of the cavity really doesn't matter, whether I'm looking at a spherical shape or whether I'm looking at a cubic or a rectangular shape. Once the cavity sizes are large, the exact shape really doesn't matter when it comes down to looking at the number of supported modes by such a cavity, right? So if I'm now looking at this object and then I ask what would be the separation, right, delta nu between the modes. And you see, I can easily get that. How will I get that? Would be, I would just differentiate delta n by delta nu, right? And this will give me 8 pi nu square, because the 3 gets cancelled there, by c cube times the volume, right? Which I can rewrite as delta nu equals to c cube by 8 pi nu square times the volume, right? And what I have done is to take my delta n to be 1, right? I'm asking what is the separation between basically adjacent modes of such a the cavity. So I have taken my delta n to be equal to 1, and that gives me that I can rewrite this as lambda cube by volume as a geometric factor that comes in, and times nu by 8 pi. What I've done is basically multiplied and divided by nu so as to identify c cube by nu cube as lambda cube. So now you can clearly see that, let us say that my lambda optical is of the order of 600 nanometers, and then imagine that I have the same volume. I'm taking that as 1 centimeter cube, right? And you can try and put this back in here, and you will see that this delta nu for such a cavity turns out to be, so this is 10 to the power of minus roughly 21, right? This is minus 7, so this is 10 to the power minus 21. This is 10 to the power of minus 6, and you have 10 to the power of 14, and of course there's a factor of 8 pi. So you will see that my delta nu comes out to be of the order of 4 hertz, right? Now you see, this is an extremely tough proposition if I want to now select, for example, a single mode, because remember that we would like to have the ability to produce monochromatic radiation in a laser. A nu of the order of 10 to the power of 14 hertz, we're trying to pick up a single mode where the next mode is 2 to the power 14 plus 4 hertz. This is a dense distribution of modes, literally millions and billions of modes which are going to be there. So for example, for a helium neon laser, if I had a 3-dimensional cavity, a helium neon laser has a gain bandwidth, right? Delta nu gain is of the order of 1500 megahertz. That would mean that essentially I have, delta nu gain by delta nu, which I calculated here, of the order of 4. So this literally I have 10 to the power of 8, 4 into 10 to the power of 8 modes possible, and to pick up a single mode for oscillation is going to be a extremely non-trivial task, right? So clearly this method of trying to confine light inside three-dimensional cavities, it's going to be extremely difficult if I want to now create lasing or create or basically intensify light at a particular mode of a particular frequency. And that is the reason you would not see a three-dimensional cavity for a laser. So in comparison, if you now look at a one-dimensional cavity, right? So let me quickly review the one-dimensional cavity. You want a L such a way that it would fit n times lambda by 2. That would mean that if I create my new n along the same lines as what I have discussed, this will come out to be n times c by 2l. So in contrast to the 3D cavity that we have just seen, you can quickly see that my delta nu here is quite different. Delta nu here is simply c by 2l, where for example this is 3 times 10 to the power of 8, and even if I look at, let's say I look at 1 centimeter long cavity, that is 10 to the power of minus 2, I will quickly get basically 10 to the power of 10 kind of a separation between modes, in contrast to few hertz. We are now looking at 10 to the power of 10 hertz. And for example, in a helium neon laser, if I have a length of about 1 meter, and for such a cavity, I can get my delta nu power of 8. That would mean that the number of relevant modes which I would get within that 1500 megahertz bandwidth, right, 10 to the power of 8, would be order of 4 or 5. Clearly you can see, if I now have a 1D cavity, that I will be able to select one mode out of these 5 to 6 modes, in comparison to a 3D cavity where I have to select one out of 10 to the power of 8 modes. So there is simply no argument in the geometric advantage that you get from going from a 3D cavity to a 1D cavity. And that, I think, is a very important lesson. And this solution of going to 1D cavity was independently developed both in the US and in Russia in the beginning times of laser. So you see, this was crucial that people thought about going from 3D confinement to 1D confinement. For completeness, I am now showing you the form of the solution of the electromagnetic field inside such a three-dimensional cavity that we discussed above. I can clearly see that the three integers L, M, and N, which correspond to the Kx, Ky, and Kz, these, at least two of them, have to be non-zero for the field to be non-trivial. If you choose two of them to go to zero, the solution will turn out to be just zero, which is a trivial solution. We are not interested in that. So you can put those factors in and convince yourself that this is indeed true, and hence the lowest order modes are indeed ones corresponding to 0, 1, 1, 1, 0, 1, and 1, 1, 0, as we described above.